One of the things that we learned is a way to calculate the speed of sound in air based on its temperature. There's a formula that's given to you. Again, I'm having some troubles with my notebook software. It keeps crashing on me. I apologize. So we're just going to scroll through this. That formula in the center of the screen here is the formula that you would be given on exams, and it's used to calculate the speed of sound in air. Is there anybody else who was not here Friday? Okay. And I apologize because I couldn't get the video up until yesterday morning or afternoon. Thank you. But there's a video of the lesson. It's posted. The link is posted in Google Classroom. You are going to, if you watch that video that's posted, you're going to lose out on a lot because we did some demonstrations in the atrium that I just edited out because you couldn't see them. There were also some demonstrations in here that I edited out because you couldn't see them. So again, you miss out on it a bit. Anyway, we can calculate the speed of sound in air at any temperature using this formula. We also learned yesterday that there is this thing called resonance. And I mean, I can show this to you very quickly again here. Resonance occurs when you have, well, let me back up. Things that vibrate at natural frequencies. There's a certain frequency that a pendulum swings at. It's based on the length of the pendulum and the acceleration due to gravity. There's a certain frequency that a mass on a spring oscillates at. It's based on the spring constant and the mass. And listen, if you put into, we didn't have time to do this last week, but if I put into my formula for period of a mass on a spring, a mass of 0.2 kilograms, and I calculate what this period is, well, can you do that for me, please? Can you calculate what we're going to get here for a period of this spring? This mass on this spring, I should say. Brooklyn, what do you got? 0.8971. 0.8971 seconds. Anybody else? Okay, good. The fact of the matter is, we can calculate a frequency from that. Do me a favor, take the reciprocal of it. Remember, frequency is the reciprocal of period. You're going to get a little over 1, but I don't know, 1.1? Well, let's call it 1.1 hertz. Listen, if you hang a 200-gram mass on a spring, and by the way, this should be newtons per meter. I was thinking of a pendulum. This is a weird one. The spring constant is 9.81 newtons per meter. It's the same as acceleration due to gravity, just a fluke, okay? I mixed up my two formulas. But if you do that and you get 1.1 hertz for this spring, and I take a spring with that spring constant, I put 200 grams on it, and I start oscillating, it's going to oscillate at 1.1 hertz. I can't just hit it a little more and expect it to change the frequency. It has a natural frequency. And that's called a resonant frequency. So the idea behind resonance is that if I had, and we can actually, I might try this. I don't know how I would set it up, but I'm curious. If I had a metal bar that could carry a little bit of vibration, okay, and I hang from it a spring with 200 grams on it, and I hang from someplace else on here another spring, and it's an identical spring with 200 grams of mass, and I get the spring on the left oscillating, the spring on the right should oscillate, should start oscillating, because the 200-gram mass on the spring on the left is going to oscillate with that frequency of 1.1 hertz, or whatever it is. It's going to cause the metal bar to vibrate with that frequency, and the metal bar is physically connected to this mass on this spring, so it will vibrate with that frequency because it can, because that's the natural frequency. So if I start this happening, that should happen. On the other hand, if I tried this, and I'm really curious, I want to actually set this up for you guys. I'll set it up tonight for tomorrow, or if I have time today, I'll see if I can rig it up somewhere. On the other hand, if I get this oscillating, nothing will happen here. Nothing is going to happen there. It doesn't even matter if I grab this metal bar and I start physically shaking it up and down at whatever this frequency of the 200 gram mass is. The other one is not going to go. Whereas over here, if I get this happening first, in theory, and I'm really curious to see, I think it should work. I need to figure out where to hang them. In theory, the second one will start going. Now, I showed this to you with sound waves, or I didn't show it to you, I guess you listened to it with sound waves, by using two tuning forks. And you can tell if these tuning forks are making a noise, even if it's very quiet, because it amplifies the sound coming out of the opening. Yes? Can you hear it already? Okay, but if you get closer, you can really hear it. So what we did was we said, now I've just deadened this tuning fork by touching it, so it's no longer vibrating. What we've said is that instead of having a piece of metal, like a metal bar connecting these, we have air. So when I get this one going, it creates a sound wave that travels through space, oscillating the air with that frequency, and when it hits this tuning fork, and I'm just giving anybody who was absent on Friday the opportunity to see this or hear it. That you get that resonance occurring. What I just showed you is called acoustical resonance. What I'm talking about up here that you're looking at on the screen, I guess we could call mechanical resonance. But the basic idea is the same. Things vibrate at a natural frequency. We also talked about beat frequency. And beat frequency has to do with the fact that if you have two different frequencies of sound occurring together, if they don't quite match up, you will hear a pattern. And I guess I will quickly show this to you again, or let you listen to it again. Right now, these two tuning forks have the same frequency, so when I get them going, together, you just hear a louder noise. There's nothing great about that. If I can alter the frequency of one of these, and we did that by attaching magnets to the top of one of them to, I guess, change the mass and the weight of those two sides of the tuning fork. So whatever force is causing them to vibrate, when I hit it, it's working on a bigger mass. And my hypothesis is this frequency will be less. I know it's going to be different, but I think it's going to be less. When I sound these two tuning forks, you hear that wobbling noise. And I figured out where to hit the tuning fork so it doesn't have that annoying buzz. Remember that from? And there were an awful lot of those warbles per second, weren't there? Like, just do that again. I would say 5, maybe even 6 or 7 beats per second. If I move these magnets down further, my hypothesis is that I'm not changing the frequency of this tuning fork that much. Because where the tines move or closer to the top, they move more. So I think I'm upsetting the natural frequency by doing it with the magnets there, but not by as much. which means these two frequencies are going to be closer together than they were in a second ago. Would you agree that's about 1 beat per second? Maybe even less. About 1 beat per second. What we learned is that these two frequencies have to be off by 1 hertz. So if this is 250 hertz, this could be 249 or it could be 251. If I go up here and I estimate that to be 7 times per second, if this is 250, then this one could be 257 or it could be 243. But the difference between the frequencies gives you the beat frequency. And that's what we did. So take a look now at all of your work from Friday. Does anybody have any questions you would like me to go over? Go ahead.
Number 6.
Okay, let's look at number 6. How deep is a lake if a sonar signal reflected from its bottom is detected 0.62 seconds after the original signal is transmitted? And sonar is a sound wave. It's a sound wave that can be used to penetrate water or air. If you've ever had a sonogram, it's using sonar. So if you, rather than an X-ray, they might use a sonogram, and it's sending sound waves through your skin. It's hitting your organs and reflecting back, and they can tell something about your organs. We have sound wave traveling through water, and it travels from the top of the water to the bottom, and it's detected 0.62 seconds after it's originally sent. What that means, Nate, is the sound travels this distance and this distance in 0.262 seconds. The speed of the wave is 1.46 times 10 to the 3 meters per second. We talked a little bit about this the other day, but forget about the formula for the speed of sound in air. Sound will travel through solids a lot quicker than it travels through air. I mean, think about having a metal bar, and I tap one end of the metal bar. There's going to be a collision occurring between the atoms in the metal that reproduces that sound traveling to the other end of the bar. But those atoms are in a solid, and they're right next to each other. They're right next to each other. So when they hit each other, it's going to be a very quick chain reaction, taking the sound down the line. We also know the time is 0.62 seconds. And this is simply a matter here of using distance equals speed times time. We're using the uniform motion formula. So let's do that. Let's take the speed times the time. 1.46 multiplied by 10 to the 3 meters per second multiplied by 0.62 seconds. Let's see what this gives us. 1.46 times 10 to the 3 is 1460 times 0.62. And you look at your answer and you get disappointed because it's incorrect. Why is it incorrect? What have I not taken into account in my calculation? But I have mentioned this. Zahar?
It's only asking for the time it gets from the bottom to the top again.
Right. So we just want the distance from the bottom to the top. And what I can do is just divide this distance that I found by 2. And that will give you the answer. Now, if you wanted to, how many of you would have divided the time by 2 and done a calculation? Maybe do that too. It doesn't really matter. Anyway, does that help, Nate? Yeah. Okay. Any other questions? Yeah. 9? Okay. At what temperature in air will the sound be 355 meters per second? Well, we have a formula that we're given that says the speed of light, the speed of sound in air is given by 331 plus 0.6 times the temperature. Is that right? Did I remember that right?
Yeah.
Okay. Again, I don't know if I mentioned it today. This would be given to you on an exam. You don't have to memorize it. So what we're doing here this time is normally you're given a temperature and asked to find the speed. Here we're given the speed. So we're going to put the speed in here. And solve this equation. And this is a two-step linear equation. This is no different than solving the equation 20 equals 12 plus 3x. We would subtract 12 from both sides of this and divide the result by 3. So I'm going to subtract 331 from both sides. And I end up with 24 equals 0.6t. Is that right? It's going to be pretty high temperature. $40. Sweltering hot. Middle of Texas in the middle of summer. Pretty warm. Does that answer your question, Zahara? Okay. Any other questions? Yeah. Number 10. Okay. A piano string and a tuning fork are sounded at the same time. The frequency of the tuning fork is 660 hertz, and there are 3 beats per second observed. I'm really glad you asked this question. I have a piano at home, and I get it tuned about every year or two. I'm not a big piano player. I just bang away at the keys, but I have friends who like to play piano, and sometimes when people are over, we get the guitars out and pianos, and we play music. But pianos need to be tuned, particularly in Alberta where the weather goes from very cold to very hot. Things stretch, things contract. And we have this guy that comes out and tunes our piano. It's this old guy. He's got to be 85 years old. And he has tuning forks. And he'll sit at the piano and he'll hit a key and he'll bang the tuning fork on his knee. And he'll listen to the sound the piano makes and the sound the tuning fork makes. And the first time I saw him do this, I was kind of like, how is he doing this? And then he tightens the string in the back of the piano or loosens it. And I asked him about it, and I realized, and I should have known, he's tuning it so you hear no beats. When he hits the tuning fork, and his tuning fork sounds like this, and that's the frequency that the string needs to be tuned to. Whoop. And he hits the piano key, and he hears that, he knows the piano is not in tune. Now, that could mean that the string on the piano has too high of a frequency, so he loosens the string. And if he's loosening the string and he starts to hear more beats per second, he knows he's going in the wrong direction. So then he'll tighten the string. I've also had people come out and tune the piano and they just have it a little electronic device, which is really pretty cool, where they hit the key on the piano and they just look at the device and it tells you the frequency. And I asked him about that and he says, that's no good. There's errors in the electronics and it's not always accurate. This is accurate. He says, music is all about listening, and that's how you tune a piano. And he's probably been doing it for 70 years. Anyway, it's an interesting application of physics. So what do we have here? We have a tuning fork with a frequency of 660 hertz. My piano tuner comes out, and I don't know if you know this is how pianos work. When you hit that key, there's a little piece of wood with some felt on it, and it hits a string. It actually plucks the string by smacking on it. And we don't know the frequency of the string, which is what we're trying to find, but we know there are, how many beats per second? 3 beats per second. This is what's called the beat frequency. And what that means is the two frequencies are off by 3 hertz. And what that means is this could be 663 hertz. It could be. So my piano tuner, my guy sits there on his stool and he hears 3 beats and he goes, no, maybe the frequency is too big. By the way, if he hits it and he doesn't hear any beats, he doesn't need to tune that string. But he hits it and hears 3 beats. He goes, well, maybe it's 663 hertz instead of 660. So what does he do? He lowers the frequency on the string, which I'm pretty sure would involve loosening the spring. Pretty sure. I think a tighter spring, I guess it's a string, right? Piano. Tighter would be a greater frequency. Absolutely, I think so, Jay. So he adjusts it. And if he decides to loosen the spring, I keep saying spring, I'm sorry. If he decides to loosen the piano string and he hears more beats per second, then what that means is this was actually 657. It has to be 3 off from the 660. So there's 2 answers here. The difference between these 2 frequencies has to give you 3. So what number could the other one be if it's 660? 3 more or 3 less? Does that make sense, Brooklyn? Okay. Any other questions? All right, we're going to take a look today at the Doppler effect. Tomorrow we are going to be measuring the speed of sound. After we learn tomorrow about something called standing waves. I did actually show you standing waves on Friday. I am not going to do that again. But those of you that were here, remember when we were in the atrium and I took that thin spring and I stretched it out. Alex was holding the other end and I twirled it. I could get it moving like a skipping rope, or I could get it moving like a skipping rope with a fixed point in the middle where I was twirling here. This part was going around and around, and this part was going around and around, and all that was happening was this was going back and forth this way, this was going back and forth that way. Remember that? It's called a standing wave. And did I get up to I didn't get up to 5, did I? I got up to 4 nodes. So I was actually able to, that was with 3. 1, 2, 3, 4. And this was a lot of work, and I want to explain to you again why. In order for me to get it to have that wavelength, which means a particular frequency, there's a certain resonant frequency for that spring. That was a spring, by the way, not a string. It was a spring. And I had to, if that natural resonant frequency to hit this, if that frequency happened to be 5 hertz, that means I have to twirl that around 5 times per second. Because that's the frequency that will produce that pattern. So in order for us to determine the speed of sound tomorrow, we're going to learn more about standing waves. In the meantime, we're going to be looking today at the Doppler effect. We're going to describe the Doppler effect qualitatively, and then we are also going to be looking at some calculation-based questions. And again, I don't know what's wrong with my notebook software, but we'll have to do this in Microsoft Word. So we're going to be calculating frequencies and wavelengths as well. Get rid of that. So the Doppler effect is used to explain why sound or light has a different apparent frequency or wavelength when the source of the sound or light is moving or when you're moving. Okay? We talked a little bit about this last week. I don't remember what day, but there was a day where I said, when you have a train moving towards you, the pitch or frequency of the sound that the train whistle makes is different than when it's moving away from you. So Some of you are not going to like this, but that's a shame. I'm going to twirl this around up top above my head. If I do that here, then some of you will not notice the Doppler effect as much. But I'm going to go over on the other side of the room and do it. But basically what's going to happen is if I twirl it around, at some point this is moving towards you, and no matter where you are in the room, at some point it's going to be moving away from you. I'm going to, in the hopes of actually recording this, I'm going to put a second microphone on the other side of the room. I don't know how well it will be recorded, but just in case somebody's watching on video, I'll just put another microphone over here. And there is no volume on this, so that's it. You got to live with that noise for a little bit. Now, I won't notice anything, generally speaking, because I'm right here. But again, sometimes this is going to be moving towards you. Sometimes it's going to be moving away from you. What you're trying to do is determine in your head what your experience is in terms of the difference between the two. Wait till I get it going well. Yes? Even for you, you're right here, right? But at times it's moving towards you, and at times it's moving away from you. Where would you say the pitch is higher? When it's moving towards you? When it's moving towards you. There's a reason for that. If you take a look at the diagram to the right, this is a diagram of a sound wave, and S is the source and O is the observer. Now, this looks like ripples in water. Keep in mind, everybody, that sound waves are actually longitudinal. But we can imagine that these lines are not ripples in water. We can imagine they are compressions of air. And the wavelength is the distance between the compressions. So I don't know, maybe I'm using 256 hertz. And the speed of the light, I keep saying light, I apologize. Maybe I'm using a frequency of 256 hertz. And the speed of the sound in the air is 345 meters per second. V equals F lambda, which we learned a few days ago, could be used to find the wavelength. Can you do me a favor and find the wavelength of that sound wave? One point something, 1.2-ish? 1.3-ish. Okay. So the wavelength is 1.3 meters. Are you with me? What that means is that if I'm standing here in this location and I turn this on, these compressions that are traveling away from me in all directions are 1.3 meters away from each other. And what happens is, this is a way to think of it, the sound pushes the air together to get a compression, and that compression starts moving away from me in all directions, and then a short period of time later, I produce another compression, and that compression is going to be 1.3 meters behind the first one. Are you still with me? Okay. But if I am moving, say, to the right, then the compressions in front of me are going to be closer together. Because, and this is going to be lost on the video, but if I lay down a compression right here and it's traveling at a certain speed, and I'm walking this way, I'm kind of not necessarily catching up to it is maybe the way to look at it, but I'm getting a little bit closer. So that compression, I lay down, it moves away from me, but I'm walking behind it, not nearly as fast. And then when I lay down the next compression, it will no longer be 1.3 meters away. It's going to be closer to that first compression. And the faster I go, the more these leading compressions get closer to each other, and the further apart the trailing compressions become. So to show this to you visually, this is what we're talking about here. It's going to repeat here right away. So that blue dot is the source of these compressions which are spreading out. If I change the velocity to 0, then this is what's happening. And if I'm standing in this position right here where the meter stick is pointing, then those compressions are going to pass me with a certain frequency that's the same as the frequency of the sound. But if this person is moving, then when those waves, we'll wait for it to start again, when those waves pass me, the wavelength of those waves will be smaller. And I hope that everybody understands when you have a smaller wavelength, you're going to have a larger frequency. So we can go back to my analogy here that I used with the actual numbers and say, let's say when you're moving, that wavelength becomes 1.0 meters. Got a lot going on here. What determines the speed of the wave? True, but the speed of the wave will have a certain value regardless of what the wavelength or the frequency is. Does anybody remember what determines specifically the speed of any wave? Yeah, what it's traveling through. And it's traveling through the same air, so the speed is still 345 meters per second. What will, if the wavelength gets compressed to a meter, what will the frequency be? Use V equals F lambda, which would mean frequency would be speed over wavelength. Well, aren't you going to get 345? You're divided by 1. So this is a different sound than this. It's a higher pitch. So what's happening here basically is when you are getting closer to the source because the source is in motion, you hear a higher frequency. And if it were summertime, we would do one of two things, and sometimes I've done them both. I would get in my truck and we would walk a block or two away out of the school zone, make sure there's nobody around. I would drive at about 40 kilometers per hour down the road, laying on my horn. And when I passed you, you would notice it. I have also in the past taken that thing that makes that noise and started on one end of the hall on a bike and pedaled as fast as I could. And when I pass you, and it doesn't matter where you are, you could all be lined up. I can be passing you at different times. And when I ask you if you're all lined up, raise your hand when you hear the pitch change. Your hands go. They start to go up in the order in which I pass you. So there's other things that we can look at. If you like, and I'm not sure how you will, if you will like this, we also have this. And the reason why you might not like this, becomes pretty apparent, doesn't it? Too much? How's that? Can you live with that? All right. Okay. You hearing a high frequency because the compressions are pushed together. But look what happens now. Now I'm in a region where the compressions are further apart, so I hear a lower frequency. And what's really important is that you simply understand that when the compressions get closer together, you hear a higher frequency. And that means, everybody, that we could have the source not moving, but you could be moving. If I'm moving closer to the source, I hear a high frequency until I pass the source. It doesn't have to be that the source is moving. I guess I could have picked a faster speed. Or they could both be moving. And that gets pretty complicated because if they're both moving, but maybe they're both moving in the same direction, this will be a higher frequency because the distance is getting closer, isn't it? But when I pass, it should be a lower frequency because I will be in the region where I'm getting further away. We don't worry too much about that. We only worry about situations where the observer is stationary. Okay? That's kind of the qualitative aspect of the Doppler effect. Does anybody have any questions about this? Doppler effect with sound. Okay, so describe the wavelengths and frequencies on both sides of the moving source with the wavelength and frequency of the sound produced by the stationary source. I'm going to clip this and put it into Notebook and hope it doesn't crash. And we can put the answers right up here on this diagram. So there is a frequency of the source and there is a wavelength of the source. Right? What does the person to the right of the source hear? A higher frequency or a lower frequency? Higher. So this will be a larger frequency, but since frequency and wavelength have to multiply to give speed, and the speed doesn't change, if the frequency goes up, the wavelength's got to go down. You know, when I take a tuning fork and I strike this tuning fork of probably 128 hertz, and you can actually see the tines vibrating, that sound has a particular wavelength. Do me a favor, let's use 350 meters per second. What is 350 meters per second? It's not that hot in here, but we'll just go with it. I like that you looked at that. What is 350 meters per second divided by 128 hertz? Okay, well, there's a way to qualitatively describe the Doppler effect, which is what we just did, but there's a way to quantitatively describe it. And it's a formula. And if you turn the page, I guess we do have a question. Oh, we already did that. If you turn the page, there's the formula. This is on your formula sheet. The formula is the frequency that you observe. The frequency that you observe can be found by taking the speed of the wave in air, the speed of sound in air, dividing by the speed of sound in air plus or minus the speed of the source multiplied by the frequency of the source. Did I get that right? Pretty sure I did, but it's a weird formula. But there's that plus or minus thing. And this is a real pain in the butt. You have some rules here, and the rules are V of the source is positive if the source is moving away from the observer. The receiver is the observer. And it's negative if the source is moving towards the receiver. Now, I am going to tell you that you do not need to memorize those things. Let's dive into the first example, and I'll show you why you don't need to memorize them, although you could if you wanted to. A car is traveling at 29 meters per second towards a stationary sound. It's a whistle. And the frequency of the whistle is 625 hertz. If the speed of sound is 337, what is the apparent frequency of the sound heard by the driver? So now we have a really big problem because the sound is stationary but the observer is moving. Okay? But what you need to appreciate is that if the observer moves 29 meters per second toward a stationary source, that's the same as the source moving 29 meters per second toward a stationary observer. In other words, with that thing I twirled around my head, if it happens to be moving towards you at 5 meters per second at some point, you hear something that would be the same as if I just held it stationary and you ran towards it at 5 meters per second. All right? So it doesn't matter which one we consider the source or the observer. What is our formula? The frequency of the observer, not of the observer, the frequency that the observer detects is the speed of the wave over the speed plus or minus the speed of the source times the frequency of the source. Well, the frequency of the source is 625 hertz. That's easy. The speed of the sound is 29 meters per second. Or sorry, the speed of the sound is 331 meters per second. No, 337? 337. I'm going to leave the units out. And then we also have on the bottom plus or minus the speed of the source. And we're imagining that the source is in motion and not the observer. But it's 29 meters per second. Now, here comes the part where you don't have to memorize whether we put positive or negative in. You have to think. Read the question carefully and answer this question for me. Will the driver hear a higher or a lower frequency? Higher, right? Okay. Now, take a look at this expression. This is a fraction. The only way we can get a higher frequency is for that fraction to be a bigger number, isn't it? Well, what do we do to the denominator of a fraction to make the fraction bigger? We make the denominator smaller. So what I'm telling you is if you put plus here, this would not give you a bigger frequency. You have to put minus there to give you a bigger frequency. And that's going to give us the answer to the question. Another way to do it, I suppose, is without thinking about it, just guessing whether it's plus or minus, getting an answer, and if you get something that's wrong because it's too small when it should be bigger, then do the opposite. 337 divided by, in brackets, 337 minus 29, end brackets, and then we have to multiply that by 625. This person in the car will hear a frequency of 683 hertz. 684, let's call it. If the car in the last example was traveling away from the stationary sound, what would be the apparent frequency? Well, everything would be the same here. It would still be the frequency heard, which is the apparent frequency, would be the 337, the speed of sound, over the 337, the speed of sound, plus or minus the speed of the motion of the observer. And again, I know the observer is stationary because that's what we're told in the question, but we can imagine that the source is stationary and the observer is moving. Times the, can't wait to get this thing fixed, 625. But we know if you're moving away from the source that the frequency will be lower. The only way to make this lower is to add the 29. So can you work that out for me, please? Have you already got it, Alex? What is it? 575 hertz. Any questions with number 2? Couple more quick examples. Let's take a look now at number 3. A whistle has a particular frequency and it's moving at 23 meters per second towards a stationary observer. The speed of sound is 342 meters per second. What will be heard? Well, this one is actually in some ways a little bit simpler than the previous one because we actually do have the source in motion. So frequency is the speed of the sound in the air over the speed of the sound in the air plus or minus the speed of the source relative to the observer times the frequency of the source. So this will be 342 over 342. Let's see, if they're getting closer together, the frequency will be greater. So the bottom number has to be smaller. Minus the 23 times the frequency of the source is 965. Can you work that one out for me, please?
Hertz.
670 hertz. Anybody else? Okay. And the final question, the only thing that would change in number 4 is we would have plus on the bottom because they're moving away from each other. So for number 4, we would have plus. Of course, that's going to change the result.
There was an error. I had put 625 again by accident. It's
Oh, so this is not 670 in the previous question? Okay.
1035.
yeah.
1035.
1035. Okay. Oh, you use the same frequency as last time?
Yeah.
Okay.
I looked and I was like, that should be bigger.
1035J? By the way, I'm not sure why I didn't mention this last time. The frequency of human hearing is as low as 20 hertz and as high as about 20,000 hertz. When you start to get up to 10, 15,000 hertz, it becomes uncomfortable. Okay. How many of you are aware that there are certain frequencies that are really bothersome for people your age? And some municipalities in Europe, I don't know if there are any in North America, in places where teenagers tend to congregate late at night and maybe cause trouble, I know not you guys, but other people, they broadcast these really, really high-pitched frequencies that most people can't hear, but younger people can, and as a result, they don't congregate there. Okay. Not only does it become uncomfortable, it can become downright painful. It would be at, say, 15, 16,000 hertz. It's causing your eardrum to vibrate so frequently that it physically is uncomfortable. It does it. Your eardrum has a lot of natural resonant frequencies, but it's not very comfortable. Okay, now if we change this to plus, and this is 965, what are we getting here?
904.
904. I have one more thing, so I'll just double check. Anybody else? Okay, good. I have one more thing I want to show you because you might encounter it someplace. Let's say that I have the source of a wave moving this way at 20 meters per second. And I have the observer moving this way at 4 meters per second. And the frequency of the sound is 1,000 hertz. And the speed of the sound in air is 340 meters per second. What will I hear? So this is difficult because I have two things moving. I would have frequency. Let me move this over a little bit. I would have the frequency I observe equals the speed of sound in the air over the speed of sound in the air plus or minus a speed, and then times the 1,000 hertz. That you know I have to have a minus there. Because the frequency that I hear has to be more. And that's the only way I can mathematically get that to be a bigger number. The question is minus what? Jay?
24.
It is 24. Because it's all about relative motion. Normally we like this to be 0, right? Because in the formula, the other v is the speed of the source. But what's important is if I'm moving towards the source at 4 meters per second, and the source is moving towards me at 20 meters per second, then we are getting 24 meters per second closer per second. I think I said meters per second. That's not what I meant. We are getting 24 meters closer every second, which means that we could do this. And that would give us the answer. What if instead, and I didn't put these in your notes, but you could reason it out, I think. What if instead that were happening?
16.
16. The whistle or the train or the sound, whatever the source, is catching up 16 meters every second. Would I still have minus here? I would, because it's getting closer. What if, so that would be 16 here. What if I did this? I better, you know what, I better show this to you. right? What if I did this? Would you agree the number would still be 16? Would it be plus or minus? It would be plus, because I am now getting 16. I am now getting 16 meters further away from the source as time goes on. So the wavelengths are going to be spread out more and the frequency goes down. So if you ever run into a problem where the observer is moving, whether the source is moving or not, but the observer is moving, just imagine what's happening if the observer was stationary. What speed would the source have to have, and in which direction would it be moving to be able to get the right answer? You can see what your assignment is. It's a bunch of practice problems dealing with the Doppler effect on the next page. Get to work on those, please, and I'll be with you shortly.